Okay, our first example is to take this structure, okay, 1-bromo, 1,2-diphenyl propane, okay, and basically when we use a strong base like sodium hydroxide, what is our product? Well, we can see here that it's going to be an alkene, but then do we get a mix of alkenes? What are we going to get? Are we going to get basically, so if we go through and take this, this is 1, 2, 3, okay, and H comes out, so this is going to be an S. This is 1, 2, 3, so that's an R. Okay. And right now we can't quite see the stereochemistry. We want to be able to draw it, so it's okay. So let's draw my. All right. Okay, so if I put my phenyl group, let's say right here. Actually, I don't want my phenyl group there. Let's put my bromine right there. Okay. Now, where is my phenyl group going? So this is S. 1, 2, 3. That's R. So 1, 2, 3. Hydrogen's coming out, so this is S. Okay. So now I have 1, and then basically if the hydrogen's in the back, so 1, 2, 3, I want it to be R. So 1 is this one, 2 has got to be 1, 2, 3 at the front. So this is my phenyl, in the back is my methyl, and this would make this stereochemistry R. See? 1, 2, 3. So you can imagine it in the back. Okay? So this is R. So now, if we take a look at my base coming in, remember, sodium hydroxide is a hydroxide. That's my base. My sodium is my counter ion. This takes a hydrogen. That forms my double bond. And that comes out. And when you do, your product, this phenyl and the hydrogen are on the same side. So your product will have a methyl on this side, a phenyl group on this side, a phenyl group here, and my hydrogen there. And this is the only product you're going to get. Okay, so this is a 1, 2, 3. So this is a prop, 1-ene. Okay, this is a 1, 2 diphenyl. Okay, and we know it's basically 1, 2, 1, 2. This is an E. 1, 2 diphenyl prop 1-ene. Okay, and that's the only one you're going to get. You're not going to get the Z, and it has to do with the stereochemistry requirements of my E2. If we take a look at the Newman projection, okay, so because we need the requirement of it being coplanar, in most cases it's going to be anti-coplanar. Under very special circumstances, if it's syncoplanar, then you can still get an E2. If it's neither, you cannot get an E2 product. So let's take a look at my Newman projection. Okay, so this is C1 in the front, and C2 in the back. And for us to get an elimination, let's see. So we need bromine, that group, and phenyl, and hydrogen. So 1, 2, 3. So bromine here, hydrogen there. 1, 2, 3. Phenyl here. So this would be an S. Okay? So I'm looking down here. Here's my bromine. Hydrogen's to my right, phenyl's to my left. Now if I'm looking at the back, okay, so let's say I want the hydrogen here. Okay, so the hydrogen's here. Let's see. 1, 1, 2. That's an S. So 1, 2. So this is my phenyl, and this is my methyl. And so in the back, so the front should be an S, and the back is an R. Okay, and we can see now that when my base comes in, pulls off the hydrogen, then it's this lobe here that now forms my pi bond. Okay, so because that's where my pi bond is going to be, I can see that my phenols are going to be, this is where my double bond is, then phenyl, methyl, phenyl, hydrogen, right there. And that's the only product, again, that you can get when you do an E2. Okay, so just be aware that you are required to have it to be coplanar. Let's do one more example for E2. And then we'll take a look at a special case of E2. So, when you look at cyclohexane systems, okay, you have to be aware of where the equatorial and the axial substituents are. So let's take this for example. Let me subject that to a strong base like methoxide. Now, to assess what kind of product you're going to get before you actually do your E2, and how do you know it's an E2? We've got a very bulky, it's secondary, but this is going to be in the way. I've got a strong base. You're going to need to take a look at your chair conformation. Okay, so let's take a look. So suppose I put my methyl group here. Then my hydrogen would be in the axial position, which means my bromine would be equatorial. This hydrogen would be axial. This hydrogen would be axial. And this deuterium would be equatorial. Okay? Well, that's all well and good, but here, no E2 can occur. Okay? So, before I do the flip the chair, let's take a look at why. I'm going to put the Newman projection right here. So if I look at the Newman projection, okay, what I have is I have my bromine at equatorial, my hydrogen, okay, at axial, okay, and then here I'm going to have my methyl, okay. So let me look at this system. Here's bromine, right? Here's hydrogen, okay? And then, if I look this way, deuterium is equatorial, hydrogen is here, goes down here, here, hydrogen, hydrogen. This one, hydrogen, hydrogen. And in this one I have my hydrogen, my methyl. Okay, my methyl is also equatorial. Okay, so something like that. Okay, so let's see if I can just draw this a little better so you can see. This isn't axial, it's a hydrogen that's axial. Okay, so here, since it's equatorial, this is so messy. Let me just draw my methyl group here. You can see being equatorial, there's nothing that's going to be anti to it, so I can't use this one. So let's take a look at chair 2. When you look at something like chair 2, the methyl is axial, hydrogen's equatorial, the bromine, okay, so the opposite side is axial, this is equatorial, the deuterium is axial, the hydrogen is equatorial, okay. Now, let's take a look at these guys. So here, the hydrogen's axial, bromine's equatorial, so that's not going to work. But here in this situation, let me just try to redraw this so it's a little easier to see. Here's my bromine, a little longer so you can see it here. Okay, well, my bromine's axial. Here I have a methyl group that's coplanar. Well, that's not going to go. So the only place I could possibly have any elimination is on this carbon. Okay? And if I look at this carbon, see what is coplanar and axial to the bromine? It's my deuterium. Okay? So, and this is just heavy hydrogen. So remember, deuterium is hydrogen too. So basically, when my base comes in, it's not interested in this conformer, but as soon as I get to this chair, which is less preferred because my methyl is in the axial position, but once it gets into that position, now I can form a double bond. So the only product that you would get is this. You would have the hydrogen, you lose the deuterium, you form the double bond here, you lose the bromine, and then up here attaches my methyl and my hydrogen. And you don't get the other product. Let's take a look at the Newman projection. So, if I do the same thing now, I've rotated this, so my bromine goes up, you see that this hydrogen goes here, this deuterium, so here's my hydrogen with the bromine in the front. Hydrogen rotated from axial to equatorial. This deuterium went from equatorial to axial. This hydrogen is now more equatorial. Methyl group is in the axial position. Okay, and all these hydrogens are the same. Okay, what we're most interested in is this part. The deuterium and the bromine are now anti-coplanar. And we can now do an E2. Okay, so that's how we handle doing an E2 on cyclohexane type systems. Okay, last E2 reaction. So we've done an E2 with strong bases and an alkyl halide. Let's take a look at a vicinal dibromide. So basically, vicinal dibromide, what's a vicinal dibromide? Remember we were talking about gem dihalides and vicinal dihalides. Okay, when they are a bond across, so 1, 2, 3, this is a vicinal, dihalide. And if I add in iodine, could be in the form of Ki or sodium iodide. The most important part is having the iodine. What this does is it takes the bromine, that lone pair forms a double bond, kicks out a bromine. So our product is my alkene plus iodine bromide, and if I use sodium and the bromide or the potassium, that you would form the salt, the bromide salt. And again, this 2 is E2. So we can use it in any cases that we've seen E2 previously, but this is also another way to form an alkene. Okay, so now let's move on to E1.